Filtration. Water filtration is a process for separating suspended or colloidal impurities from water by passage through a porous medium, usually a bed of sand or other medium. Filter classifications. Numerous ways of classifying filters. Gravity filters. Filters that are operated using gravity flow and operate in a downflow mode. Filtration rate is the flow rate applied to the filter divided by the surface area of the filter bed. Slow sand filters, rapid sand filters, high rate filters, or pressure filter. The last classification method is based on the type of media used in filter. Single media or monomedia filters have only one type of media, which is typically sand or crushed anthracite coal. Dual media filters normally consist of a layer of coarse anthracite coal above a layer of sand. Multimedia filters, such as trimedia filters, consist of a layer of coarse anthracite coal above a layer of sand and a layer of garnet or ilmenite below the layer of sand. Suspended solids removal mechanisms. There are several mechanisms involved in removing suspended solids during granular media filtration. This includes straining, sedimentation, flocculation, interception, biological growth, impaction, adhesion, and sorption. The objective is to use the entire volume of media for removing particulate matter. This is known as depth filtration, and it is more effective than just the removal accomplished by surface straining. Figure 6.25 shows illustration of 6 particle removal mechanisms during filtration. Filter media. The effective size and uniformity coefficient are two key parameters in specifying filter media. Effective size is determined from a sieve analysis curve and represents the media for which 10% by weight of the grains are smaller. Uniformity coefficient is a measure of the size range of the media and is defined as the ratio of D10 over D60 sizes that are determined from the sieve analysis curve. Table 6.12 shows properties of filter media. Schematic showing the media configuration of sand, dual media, and mixed media filters. The effective size, uniformity coefficient, depth of media, and depth of media to effective size ratios for various types of filter media are presented in the table. Single media filters typically consist of 24 to 36 inches of sand supported by 15 to 24 inches of layered gravel and are commonly used in the United States. Dual media filters consist of 18 to 30 inches over 6 to 12 inches of sand. Mixed media filters consist of 18 to 24 inches of anthracite, 6 to 9 inches of silica sand, and 3 to 4 inches of garnet. Dual media filters using GAC often use 12 to 48 inches of GAC over 6.18 inches of silica sand. Deep bed monomedia filters generally use silica sand or anthracite with an effective size of 0.5 to 6 mm, UC from 1.2 to 1.5, and a depth of 4 to 6 feet. Typical filtration rates for various types of granular media filters are presented in Table 6.14. According to Castro et al., most regulatory agencies will not approve filtration rates exceeding 4 to 5 GPM per feet squared. Granular media filtration. The primary goal of granular media filtration is to use the entire filter bed for solids removal rather than being strained at the surface. Cross-sectional view of a rapid sand filter during filtration. Darcy-Weisbach equation. Karman-Kozeny equation for head loss across a clean filter bed. Rose equation. These equations are the head loss equations developed by Rose for uniform particle size and mixed particle size. Equations 6.135 and 6.136 are the head loss equations developed by Rose for uniform particle size and mixed particle size, respectively. Equation 6.137 is used to calculate drag coefficient. Equation 6.138 is used to calculate the Reynolds number. Ergon equation, the most widely used empirical equation for estimating head loss in clean granular media filters. Head loss coefficients for use in Ergon equation. Backwashing of filters. Periodically, granular media filters must be backwashed to remove particulates and turbidity that build up during the filter run. Operators backwash a filter based on one of the following scenarios. When the head loss through the filter reaches 8 to 10 feet. When the turbidity in the effluent reaches a specific level such as 0.20 NTU. When the filters has been in operation for a specified amount of time. Backwash water at a rate of around 15 to 20 GPM per feet squared for 15 to 20 minutes is required to properly expand and clean a dirty filter. Cross-sectional view of a rapid sand filter during the backwashing process. Backwash hydraulics. During backwashing, the water flow through the filter bed is reversed, thus expanding and fluidizing the bed. The porosity of the expanded bed could be estimated using this equation. Drag coefficient equation proposed by Rich. Filter arrangement. Filters are typically placed adjacent to one another along one or both sides of a pipe, gallery, or gullet. Filter arrangement. Rapid sand filters are usually rectangular in shape, with an average length-width ratio about 1 to 25 and surface area ranging from 450 to 4,500 feet squared. Conventional gravity filters use length-to-width ratios of 2:2 to 4:1. Surface areas of gravity filters typically range from 250 to 1,000 feet squared, and filter depths range from 12 to 20 feet. For large water treatment plants processing over 20 mgd, filters are composed of 2 cells per filter, with a gullet running down the center. For water treatment plants processing less than 2 mgd, a minimum of 2 filters should be used. If the capacity of the WTP exceeds 2 mgd, a minimum of 4 filters should be used. For large water treatment plants processing over 20 mgd, filters are composed of 2 cells per filter with a gullet running down the center. Disinfection. Disinfection practice at water treatment plants has traditionally been the use of chlorine gas as the primary means of killing pathogens in water. Chlorine is both an economical and effective disinfectant. However, there are some concerns with using chlorine, especially hazards associated with transporting a toxic gas to the treatment site and disinfection byproducts produced such as trihalomethanes and haloacetic acids, among other chlorinated organics that may be potential carcinogens. Goal of disinfectant. The primary goal of disinfection is to inactivate pathogenic organisms such as bacteria, protozoa, and enteric viruses that may be present in the water. Microbial pathogens of greatest concern are protozoan cysts associated with Giardia lamblia and Cryptosporidium parvum, and various enteric viruses which may be resistant to specific types of disinfectants. Regardless of which disinfectants is selected, it is preferable to remove as much turbidity as possible before applying it. Major disinfectants in water industry. Chlorine gas, combined chlorine such as sodium hypochlorite, calcium hypochlorite, chloramines, monochloramine, dichloramine, trichloramine, chlorine dioxide, ozone, ultraviolet radiation. Chlorine dioxide is a powerful oxidizing agent that has been used primarily to remedy taste and odor problems in drinking water. Chlorine dioxide must be generated on-site by mixing solutions of aqueous chlorine. Ozone, one of the strongest oxidants and disinfectants available. It is an allotropic form of oxygen that must be generated on site, typically by passing clean dry air or oxygen through a high-strength electrical field. Ultraviolet radiation, generated by mercury vapor arc lamps in a non-chemical means of disinfection. UV radiation in the range of 245 to 285 nm is effective against bacteria and viruses. UV lamps are placed inside of quartz sleeves which are then placed into the water.